Okay, in this video I've got another optimization problem. This time we have a box that has a square base and an open top. I'm going to go ahead and underline that because that's going to be important. It's going to have an open top. It must have a volume of 32,000 cubic centimeters. Find the dimensions of the box that will minimize the amount of material used. So I've got some box here, and we're going to pretend like this is a good looking box, but I've got a box that's going to have to have a volume of 32,000 cubic centimeters, and I know that the top is open, so I'm just going to go ahead and kind of fill this in as if it, did not have a top to it. Okay, so I've got this square box with no top. Okay, so what am I trying to do? I'm trying to minimize the amount of material used. Well, if I'm making a box, then the amount of material constitutes the area of the box, right? So I'm again trying to minimize surface area. But this time I don't have a cylinder, I've got a box, which is probably a little bit easier to work with. Since it is a square base, I'm going to call this width, and that means that this would also be width on the bottom here because it is a square base. It's not necessarily a cube though, okay, it just has a square base to it, so that means that it could have some other height to it. Okay, it doesn't have to be a cube. That's a really important thing there because some people see square base and automatically think this needs to be the same dimensions everywhere, but it doesn't. Just the base has to be a square, the height could be something else. Okay, so surface area. The formula that I'm going to try to minimize, the area of this would be, let's see, we would have a W squared, and I only have one of those, right? I've only got this area. That's going to give me, the area of the bottom, and I don't have a top. So, I could, if I had a top, I would want to make this 2W squared, but since I don't, it's just W squared plus the area of all the faces, and there are 4 of them, right? I've got the back, I've got the right side, the front, and the left side, and so the area of each one of those faces is going to be width times height, and I have 4 of them. Okay, I want to be able to get rid of height, right? I only want one variable over here. So constraint formula, my volume needs to be this. So if my volume has to be 32,000 cubic centimeters, the volume of this box would be the base, the height number of times, so W squared times H. That needs to equal 32,000. Solve for H, so H is going to be 32,000 divided by W squared. Again, once I have that solved for H, I can then replace that in my formula for H. And so I would have that my area would need to be W squared plus 4 times W times replacing H with 32,000 divided by W squared. Okay, so let's simplify this a little bit before we take the derivative. Obviously I can't really do anything with that W squared. What I can do here is I can do 4 times 32,000, and I can get rid of this W and one of those on bottom, and so that's going to become W squared plus 4 times 32,000 would be 128,000 over W. Okay, again, if you have any variables on bottom, it might be beneficial when you're taking the derivative to make that W to the negative first. Okay, now we take the derivative and we get A prime to be 2W minus 128,000 W to the negative second. And then I'm going to rewrite putting that back on bottom. So 2W minus 128,000 over W squared. Okay, and now I want to find where this thing is 0, right? So I want to set this equal to 0, which means I need to factor this. So to factor, we would, again, like I did with the cylinder, I'm going to factor out a 1 over W squared. But instead of 1 over, I'm going to do 2, because I can factor out a 2 from the 2 and the 128. So I'm going to factor out a 2 over W squared. And that means that this term, the 2 is gone. I need it to end up being W, which means this needs to be W cubed. Right? W cubed divided by W squared would give me W. Minus, again, I factored out a 2 from the 128,000, so it's going to be 64,000. And I already took out the over W squared, so that's gone. So I have that equals 0. Again, I would want to kind of set each one of these things equal to 0, but just like with the can, this will never equal 0, because the top is a constant, therefore that will never be equal to 0. I don't need to worry about that. I need to take W cubed minus 64,000 and set that equal to 0. Add the 64,000 over W cubed equals 64,000. Cube root both sides. And W would equal the cube root of 64,000, which is 40. Now, I don't necessarily know that W is correct. I always need to do the first derivative test on that to make sure that we have a minimum. I am trying to minimize my area, so I put 40 on the number line. I go to my most factored version of this, which is right here, and I plug in something to the left of 40 again, making sure that I stay inside the constraints. So obviously W, the width of this box, cannot be 0 or less than 0, so I'm going to plug in 1. 2 over 1 squared is positive, and 1 cubed minus 64,000 is definitely negative, so I get a negative, which means I'm decreasing. Pick something bigger than 40, like 41. 2 divided by 41 squared, that's still positive. And 41 cubed is bigger than 64,000, so when I subtract 64,000 from it, I still get a positive number, which means this is positive, which means we are increasing, making this a minimum for W. And so I come back over here and I say, all right, I know that W needs to be 40 centimeters, since this is centimeters. W needs to be 40 centimeters, so what does H need to be? What's the height of the box? I just know that this is 40 by 40 on bottom. And the height, I go back to when I solved my constraint formula, the height was 32,000 divided by 40 squared. And if I do 32,000 divided by 40 squared, I get 20 centimeters. So a box that's 40 on the bottom, 40 centimeters across and deep, and 20 centimeters high, will be a square box with an open top with a minimized surface area that still holds a volume of 32,000 cubic centimeters. Okay, so hopefully you'll notice that that process that we do is about the same every time. What changes are the formulas, the constraint formulas that we're given, and then actually working through the derivative part is pretty much the same. I mean, varying in difficulty, but the same process every time.